All right. Okay, let's get started. All right. Well, how's everybody doing? It's week 3. Okay, so this week I want you guys to form teams for the final project. So we'll say like teams of like 3 or 4, no more than 4 though, okay? Even 4 is pushing it a little bit in my opinion, because I don't know. I've had group projects and we know that not everybody carries their weight equally on a group project, but anyway, I think a group you'll do a group project for the final project, and so this week I want you guys to establish a team, and I guess I'll create like a Google spreadsheet. All right, guys, please. I'll create a Google spreadsheet where you can put your team members' names and come up with a team name, and then we'll just get you guys started, at least in terms of thinking of some kind of analysis project. Okay. On Friday we talked about NumPy, and there's a lot more to talk about in NumPy, so we'll go over a bunch of stuff here. Okay. And so this is what we'll do. Okay, so as always, import NumPy as NP, and then we can do some basic math. All right. So I just pushed this version of the notebook onto GitHub, and then you can download and run and follow along. Okay, so we'll just create a NumPy array 0, 1, 2, 3. All right, and then and you can do basic math. So what are the element types? Like this 0, what is that? Is that a integer or a float? It's an integer. Okay, so when you call a range, it's going to be integers, and then you could just do basic commands like add 5, and you're going to add 5 to every number. I think if you're coming from R, these behaviors, none of it is going to be surprising, okay? You subtract 5 from each element, multiply each element by 2. When you do division, anytime you do division, the result is a float, okay? Even if it divides evenly. Okay, but in this case we got floats, and so as soon as one element in an array is a float, the whole array becomes a float. Okay, you can take the negative of the thing, you can square all the numbers. Modulo division returns the remainder, and those will be integers. Okay, and you can apply functions like absolute value functions. Okay. So those are your basic things. All right. You have trig functions. All right. So here, linear spaced from 0 to pi 3. So we got 0, pi over 2, and pi. Maybe I should do, what do I want? Quarters. So pi over 4. Pi, so how many is that? 1, 2, 3, 4. I need 5. Let's do that. Okay, so sine of theta, you get 0, root 2, 1, root 2 over 2, and 0. Okay, almost 0. Okay, same thing with cosine. Okay, so 1, almost 0, and back to 1. And then with theta, you got 0. 1, infinity, or practically infinity, -1, and practically negative infinity, okay? And of course, we're dealing with floating point numbers, so 10 to the 16 is not anywhere close to infinity. I don't even know what could be considered close to infinity, but it's a big number compared to other values, but you know. Okay. All right, and then so you've got log and exponential functions also. Oh, okay, yeah. So one thing to note is that the sine function, you call it by calling np.sine. It's not just sine of theta. It's a function within NumPy, because I don't think so. Because there's a lot of functions in Python that just don't exist. Like in R, we take for granted that I can just type in sine or log or whatever, but they don't exist. Okay, so anyway, we'll create an array of 1, 10, 100, and you can get the logs. Okay, the log function, like R, will be the natural log, and if you want log base 10, which is the common log, which is what your calculator calls log, will be log 10, okay? And then we get exactly what we expect, 0, 1, and 2. And so, you know, dealing with logs turns everything in multiplication into addition. There's been a bunch of studies that humans think in logs, and it's used against us all the time, marketing and stuff. So, for example, the idea of paying $4 for a candy bar seems outrageous to us, right? Because you're used to paying like around $1 for a candy bar, and so the idea of paying $4 for a candy bar feels outrageous, and you get angry when you go to Disneyland and you have to pay, you know, $4 for a candy bar. But then, but if you're buying like a computer, and then you see the same computer advertised, like, you know, you spend $1,000 on a computer, and then you know, the next day you see the same computer advertised for $20 less, nobody feels upset about that, okay? Even though the difference between $1 and $4 is only 3, and the difference between the $1,000 and the 980 is $20, which is definitely more than 3. And as far as your bank account is concerned, the actual numbers is what matters, not the multiplicative difference. But nobody cares. So, so anyway, they take advantage of you when you buy big ticket items like a car. They'll stick on all these options, and you'll just be like, oh yeah, I'll spend an extra $800 for the convenience package. Even though, you know, for anything else, if it's just like, are you going to spend $800 on this? Well, anyway, okay. So people think in logs. Exponential functions, you can do that. 2 to the y, e to the y, 2 to the y, and then you've got the power function as well. Okay? And so all of these are preceded by np.power. There's a whole bunch more functions, like you can always look up NumPy math functions, right? And just click mathematical functions, brings up the NumPy documentation, and there's a bunch of these, right? You guys remember the hyperbolic functions? I couldn't tell you how they work at all. I don't remember. When was the last time I used this? I just remember the bridge with the suspension cable, right? I don't know. Okay, anyway. All right, so here, aggregates. You have, Python has the sum function, but np.sum is probably what you'll want to use when you've got a NumPy array, right? Okay, and so here, a range, this will create the integers 0 through 99, right? Okay, and then when you add them up, you get 4950, 100 shy of Gauss as a child, that story. You guys know that story? Gauss I don't know. So Gauss, the guy who made the normal distribution, Gauss, or we should say the Gaussian distribution. When he was a kid, his arithmetic teacher was like, all right, guys, I didn't have a lesson plan for you. So everybody write on your piece of paper 1 through 100 and then add up all those numbers. And then, you know, Gauss being the genius, he's like, let me think about this for a bit. And then, and he's like, oh, okay, I can just pair 1 with 100, 2 with 99, 3 with 98. Everything's 101. Multiply that by 50. And I get, 50-50. So anyway, that's basically what we have here. All right, we've got np.sum, and it gives us the same thing. All right, so why do we care? All right, it's faster, and so in Python you have these special functions called it's like %timeit, and then when you give %timeit, you give it an operation. So here I'm creating a big array with random numbers, 10,000 random numbers, right? And then timeit will just say, all right, add up all 10,000 numbers using this command, add up all 10,000 numbers using numpy's sum command. Okay, it takes a little while to run, and because it's doing a whole bunch of these operations, okay? And so here we have 1.13 milliseconds plus or minus 167 nanoseconds per loop. At least that's my machine. I don't know about yours, okay? And it did standard deviation of 7 runs, 100 loops each. And then with the NumPy, it's on the order of 11.4 nanos. Oh, I'm sorry, these are microseconds, not nanoseconds. Microseconds, and it did 100,000 loops of 7 runs. Okay, so anyway, this is on the order of, what is this? 1,000 versus, this is on the order of 100 times faster, the NumPy sum for a big thing. Okay. Similarly, we have min and max functions. Okay, so there's the regular old min and max function. This will find the smallest number and the biggest number for, with 100,000 values, randomly uniform from 0 to 1, we're getting something on the order of 7 to the, minus 10 and 0.998, okay? You get the exact same values with NumPy, and again, if we time these out using the %timeit function, you can do this. So if you're curious about if you're, removing a loop or whatever has optimized, made your code faster, you can use timeit to measure. Okay. So again, on the order of 1 millisecond versus 9 microseconds. So this is like on the order of another 100 times faster. Okay. For if you have a matrix, okay. So here I'm just for reproducibility, I'm setting a seed. I'm taking the value integers 0 through 11, and I'm going to shuffle them. Okay, so this is an operation that comes from random, NumPy random.shuffle. We'll shuffle those 12 values, and then I'll reshape them into a matrix, 3 rows, 4 columns. Okay, so this is just what I happen to get. All right, the sum function, the regular old sum function, applied to a matrix will give me column sums. Okay, when you take that, you get because it basically sees it as 3. Because it almost, if you look at the I don't know, the way this thing is structured, it's like 1 row of 4, another row of 4, and another row of 4. And so calling sum on that will just take those 3 rows of 4 elements each, and then sum them element-wise, and we get 14, 8, 12, and 22. Okay, so just 10, 7, 5 gives us 22. NumPy.sum, okay, this behaves differently, and for NumPy, when you give it a matrix, it just adds up all the numbers and returns 1 value only. So we get 66. Okay. you can get the same thing. You can get row and column sums, and you just have to specify the axis. So if I do np.sum axis equals 0, okay, it will sum over the rows, so you get column totals. Okay, so axis equals 0 will sum over the rows. Okay, because when you specify the dimensions or the shape of a matrix, it's number of rows first, then number of columns. So when you say the axis is equal to 0, that's the axis that it's using for the summation. Okay, whereas over here, axis equals 1 will sum over the columns, and you'll get row totals. And so you get 2, 3, 4 plus 10 gives you 19. 1, 6, 0, and 7 will add up to 14, and the other numbers 11, 9, 8, and 5 add up to 33. Okay, you can apply other of the NumPy aggregate functions like min and max, and I don't know, whatever else we have, right? Standard deviation, okay? Standard deviation is the standard deviation of all 12 numbers, and you could ask for standard deviation applied over the rows, so you'll get the standard deviation of each column, okay? And np.min applied to axis equals 0 will give you the minimum value in each column. So, the smallest value in this column is 1, the smallest value in this column is 3, the smallest value in this one's 0, and this one's 5. So you have these values as such. Print them out. Is that okay? I think so. Without an axis specified, it'll give you this aggregate or summary function applied to all the numbers in the matrix, and then you can specify an axis, right? And this applies to any array, really. So generally, I think in matrices, but if you have like a three-dimensional array, you can specify axis 0, 1, or 2, and it will operate that way as well. Okay, so you have nan in as a float value, right? So nan being not a number, this will be like the result of doing 0 divided by 0 or something like that. Or maybe, I don't know, a 0 over 0, but like infinity divided by infinity will result in not a number. Okay, you can directly create a nan object by saying, float and then in quotes nan, and that will create not a number value. And the type of this object is a float. But and this is one of the, I don't know if it's a shortcoming of Python, but it's just one of the differences between Python and R is that there's not a designated missing value. So one thing that makes R very unique for other languages and why statisticians love it so much, one of it is the existence of the NA type for each type of variable, right? You got NAs for logicals, NAs for integers, NAs for floats, NAs for strings, meaning it's not, it's a missing value, okay? And that doesn't exist in Python, okay? In Python, we'll often use the float nan as a missing value, okay? Which just means, you're not able to do have like a direct missing value, like as a NA in string things. You'll need to have some kind of symbol that says when you see a dash, that means missing or something like that. Okay, and if you want missing integers, you got to kind of upcast them to floats, and so on and so forth. Okay, so anyway, if you do operations where you have, you're dealing with infinity and you do infinity divided by infinity, you get nan. I'm curious, what happens if I do 0 divided by 0? Okay, that just gives you a division by 0 error. Okay. So, all right, not that big of a deal. Okay, and then if you try to add not a number value with a real number, you get not a number. Okay, that makes sense. Okay, and then, but you also have the NaN safe version. Okay, so you have np.sum, and then you have np NaN sum, meaning some of the values that aren't NaN, right? And so here you get 2.0 because 2, when you try to combine it with a float, the 2 gets upcast to float type, and so not a number added to 2. In this case, it just throws away all the missing values, and you get 2 for the sum. Okay, and so here's a table that I just copied from somewhere on the internet, and okay, so you've got sum, product, mean, all of these things. And then almost all of these have the exact same thing for NaN sum, NaN product, NaN mean, and stuff like that. Okay. All right. Now we have something called broadcasting. Okay. Broadcasting is basically element recycling, but it only works if the dimensions match up. Okay, so here I have A being 1, 2, 3 and B being 4, 5, 6, and if I add them together, I get 5, 7, and 9. That's no surprise because it's just doing element-wise addition. So there's no broadcasting going on here, okay? And if I say C is going to be the elements 7 and 8, and I try to add A to C, okay, R would take this and just do 1 plus 7, 2 plus 8, and then it would do the 3 and recycle the 7 and give you 10, okay? Python's like, that doesn't make any sense. Why would anybody do that? And so it kicks back an error, okay? Because it says you can't broadcast with shapes 3 and 2. Okay? So again, take a look at A. I've got 1, 2, 3. And E is a matrix of 1, 1, 1, 1, 1, 1, 1, 1. Okay? And so here, if I say take E and add A to it, then what happens is A gets, it's known as broadcast, okay? So E is a 3 by 3 matrix, A is a vector or an array with length 3, okay? When Python sees this, it's going to say, okay, I've got to, they call it broadcast, I've got to broadcast A to be a matrix of matching dimensions, 3 by 3. So it's going to take A, multiply, or not multiply, but just basically duplicate these rows. So you're going to have another matrix that's 1, 2, 3, 1, 2, 3, 1, 2, 3. Adds those together and you get this matrix 2, 3, 4, 2, 3, 4, 2, 3, 4. Okay? This is, you're coming from R. It's probably not surprising to see it like this. Okay? Except what's the difference? If we did this in R, if I said take matrix E and add A to it, how would R's result be different? Yeah, it would be column-wise, and it would be 2, 2, 2 on the top, 3, 3, 3 in the next row, and 4, 4, 4 on the bottom. Okay, whereas Python kind of does things row-wise. Okay, but here we can reshape A to be 3 rows and 1 column, and now I can add E and A together, and we would get, again, this column matrix or column, column matrix get broadcast, and we get 1, 2, 3, and it gets duplicated as such, and we get 2, 3, 4, 2, 3, 4, 2, 3, 4. Okay, and again going back, A is here. A is still 1, 2, 3, and B is still 4, 5, 6. And so if I vertically stack A and B, V stack will stack row, vector A, the array A on top of array B, and we're going to get a 2 by 3 matrix. Okay. And then if I say add vector or add array A onto this thing, okay, it gets broadcast across the rows. So we're going to get 1, 2, 3 added on top of 1, 2, 3, and then we're going to take A again, which is 1, 2, 3 added on top of 4, 5, 6, and we get 2, 4, 6, 5, 7, 9. Here is array C. Array C has 2 elements, 7 and 8. Okay. If I try to just add this, okay, Python's default behavior is to go row-wise, and so it complains that there's a mismatch. Okay, because D again is this 2 by 3 matrix. If I try to add 7 to 8, it complains. Okay, but if I reshape C so that it's a column, okay, 7 on top of the 8, then I can add these together, and it will add D, which is 1, 2, 3, 4, 5, 6 up here, and it will add 7 and 8 to 1, 2, 3, and then 8 to 4, 5, 6. Right. So so basically, you're probably familiar with the recycling nature of R. Maybe not. Okay, Python does something similar, but it requires that the elements match, and it defaults to row-wise behavior. Okay, and this might be the craziest version of broadcasting, because R doesn't have anything like this. Okay, so here E is going to be reshaped to be a column vector or column matrix, 10 rows, elements 0 through 9, 10 rows, 1 column. Okay, and then F is just an n-dimensional array, length 11, 1 dimension. All right. You can actually add these together, and you're not going to get an error here. Okay. So what happens is that E and F will get added together. Python will see E and say, "Oh, you're a single column." Okay, and F is a single row, and so it's going to broadcast E so that it's a matrix, a full matrix, 10 rows, but now 11 columns, and then it's going to broadcast F. So it's going to have, it's got 11 columns, and it's going to duplicate it so there's 10 rows of it. All right, and so when you do this, it adds everything up like this. Okay, and you get, I don't know what this is, but you get the numbers 1 through or 0 through 19, but arranged as such. Okay. Similarly, E and F, these row and column, column vector and row vectors, they get broadcast into full matrices, and here you get element-wise multiplication, and now you have the times table, okay, for 0 through 10 and 0 through 9. Is that okay? All right. We've got Boolean operators, just like we would expect. So here's X, the digits 0 through 5. You can ask, are they less than 3? You're going to get Boolean trues and falses. Okay. Greater than or equal to, are they exactly equal to 3? Okay. And then you can, just like in R, you can take the results of a Boolean operator and subset it, and it'll only return the elements for which it's true. Okay, and again, because everybody here is coming from, or at least has experience in R, this should come as no surprise. Okay. And then again, you can apply a sum to a Boolean vector. I always want to say logical, but in Python it's Boolean. You can sum it to a Boolean array, and you'll get the count of the trues. And then again, you can also do mean, and you'll get the proportion that's true. Okay, so I think these are all functions that we're accustomed to seeing. Okay, works the same with matrices. Okay, so you can apply a Boolean function to a matrix, and you'll get a bunch of trues and falses, sum, and then also you can apply the sums row-wise and column-wise as well. Okay, just like before. And then you have element-wise Boolean operators, okay, which it basically does, your element-wise combinations, okay? So you have and, or, this is the exclusive or, and this one is probably the weirdest one to get used to. This is how you say not, okay? We're accustomed to probably seeing like the exclamation point for nots. It's tilde in Python, okay? This one always, I'm like, why is my exclamation point not working, okay? This is what we have, okay? So you just take the things. All right, and then any and all, same thing, same as what they do in the R language, right? Are any of them true? Are all of them true? All right. And then fancy indexing. So regular old Python doesn't support this, but NumPy does, okay? So if you got some kind of array here, you can say, I only want element 0, element 1, and element at index 5, and it'll pull them out, okay? And then, and similarly, if you have a matrix, you can say, I want only the elements in basically row 0, column 2, index 2, row 1, column 1, and row index 2 and column index 3. Okay, and you can specify it that way. So here, that will pull out basically exactly. So you can specify things that way. So you subset using rows and columns. All right, and then we have sorting. Okay, and we're used to sorting. I don't know if you ever used order, the order function in R, but you have the parallel argsort. Okay, so here, if x is 24130, I can call sort on x, and it will sort it in place. Maybe I should write that. Okay, sorts x in place. So so x is modified right there. Okay, let me. So here is y 5214. You can call argsort on it 2130. Okay. And this means if you want to arrange them from least to greatest, the order that you would use it will be, pull index element 2, index element 1, index element 3, and then index element 0 to get them in order from least to greatest. So it's kind of like the, I don't know, what do you need to, what order do you need to use to get them in arrangement from least to greatest? Okay, and then and likewise, you can also sort each column of x. All right. So this is going to modify this, and so here, when you have a matrix and you call sort on axis equals 0, it doesn't see these as a data frame where each row is associated. It's just going to say, I'm going to sort this column 5157 and I get 1557. I'm going to take this column, these 4 elements, 8, 7, 2, 9, and I'm going to return 2, 7, 8, 9. Okay, so it doesn't see any kind of relationship between the elements in the rows or columns, and it just does it. Likewise, you can do it on axis equals 1. Oops, and this will be sort each row of x. Okay, and there you go. Okay, we'll end there. We'll see you guys on Wednesday.